Okay, class, we're ready for 7.3 now. 7.2, remember we spent verifying identities, and we didn't really add any identities to our list of identities that we've committed to memory. We are adding some identities to our class now here in this section, but these are not really identities that you're probably going to need to commit to memory. So you can see a list of what's called sum or difference identities over here on the left-hand column of this paper and on your notes. They're called sum or difference identities because they apply when we have the sum or the difference of two angles, and then we're taking the cosine, sine, or tangent of that. Now you might wonder, why would I want to do that? We'll talk about that in just a moment. But you can see here the sum and difference identity for cosine goes like this. Cosine of the first angle, cosine A, cosine of the second angle, and look at the signs here in the middle. Notice over here we've got plus minus, and here we've got minus plus. That means whatever the sign is over here on the left, it changes over here on the right. If it's plus, then we have minus on the right. If it's minus, then we have plus on the right. And then it's sine of the first angle, sine of the second angle. Okay, with this second identity, the sum or difference identity for sine, notice the signs in the middle stay the same. And the sum identity for sine goes like this. Sine of the first, cosine of the second, cosine of the first, sine of the second. And then here's the one for tangent. So tangent of the first, the sign in the numerator stays the same, tangent of the second, then on the bottom 1, and then that sign changes, and tangent of the first times tangent of the second. Now why would we ever need these type of identities? And the answer is, sometimes we cannot find exact trig ratios because we don't have angles that are on the unit circle. We don't know right now what the cosine of 15 degrees is because 15 is not on the unit circle. So what we're going to do is we're going to try to build that 15 out of two angles that are on the unit circle. You say, what do you mean by build? I mean we're going to add or subtract two angles that are on the unit circle that will give us 15. Now we have several different choices for that. We could choose 45 and 30. That's the one I'm going to use here. So I'm going to think of this as cosine of 45 minus 30. Now that's not my only option. I could have chosen 150 minus 135, or 135 minus 120, or 330 minus 315, or a whole bunch of different things. Any of them would work, just like this one's going to work. Okay, so now what I can do then is I can apply this top identity up here, and by doing so I'll be able to get an exact value for cosine of 15. So how's that identity work? What do we say? Cosine of the first, cosine of 45, cosine of the second, cosine 30, and the sign changes on this identity. So since it was minus right here, then down here we're going to use plus, and then it's going to go sine of the first, sine of the second. So sine 45, sine 30. Okay, now it's just taking those values off of the unit circle. We know that cosine at 45 is square root of 2 over 2. We know that the cosine at 30 is square root of 3 over 2. Plus, we know that sine at 45 is root 2 over 2. We know that sine at 30 is 1/2. So I have root 6 over 4 plus root 2 over 4 which many times is then combined just to make root 6 plus root 2 all over 4. So what's the cosine of 15 degrees equal to? Well, that's what it's equal to exactly. Root 6 plus root 2 all over 4. Okay, now I'm going to erase that and get a little more room. Well, now we're ready for this cosine at 5 pi over 12. Well, now we're in radians. Okay, so we need to find a couple of angles on the unit circle that add up to 5 pi over 12. So if you think about this, here's the way I usually think through this. I think, well, what are a couple angles that add up to 5 pi over 12? Well, 1 pi over 12 plus 4 pi over 12 add up to 5 pi over 12. But those don't really, I don't know why I wrote 3 there. Those don't really help us, because while 4 pi over 12 reduces to pi over 3, which is on the unit circle, pi over 12 is not. But if I think of 5 pi over 12 as 2 pi over 12 plus 3 pi over 12, 2 pi over 12 reduces to pi over 6, which is on the unit circle. 3 pi over 12 reduces to pi over 4, which is on the unit circle. So we could turn this into a problem where I'm going cosine of pi over 6 plus pi over 4, and now I can apply the sum identity for cosine again, which would go cosine pi over 6 cosine pi over 4 minus sine pi over 6 cosine pi over 4. Cosine at pi over 6 is root 3 over 2. Cosine at pi over 4 is root 2 over 2. Minus sine at pi over 6 is a half. Cosine at pi over 4 is root 2 over 2. So this time it looks like I'm going to end up with the square root of 6 minus the square root of 2 all over 4 for the cosine of 5 pi over 12 radians. Okay, now example 3 is a sine problem, so we haven't done one of those, so maybe we'll knock one of those out real quick. If you're going to build 75, again, there's a few different ways you could do that. 135 minus 60 would be 75. Probably the easiest thing to do would just be take 45 plus 30. Now let's apply the sum identity for sine. Which was this identity here. Sine of the first, cosine of the second, middle sine stays the same, cosine of the first, sine of the second. Okay, so what did we just say? Sine of the first, sine of 45, cosine of the second, cosine 30, sine stays the same in the middle, plus cosine of the first, cosine of 45, sine of the second, sine 30. And now it's a unit circle problem again. Sine at 45 is root 2 over 2. Cosine at 30 is root 3 over 2. Cosine at 45 is root 2 over 2. Sine at 30 is a half. And this time we're at the square root of 6 plus the square root of 2 all over 4. Okay, well let's do this tangent one. To make 7 pi over 12, I'm going to try 3 pi over 12, which would reduce to pi over 4, plus 4 pi over 12, which would reduce to pi over 3. So that should get us somewhere. So we're going to take the tangent of pi over 4 plus pi over 3. Okay. Now, let's remember how the sum identity worked for tangent. It's tangent of the first plus tangent of the second over 1 minus tangent first times tangent second. So, what was that? Tangent of the first, tangent of pi over 4, plus tangent pi over 3 over 1 minus tangent pi over 4 times tangent pi over 3. Alright, so let's do some unit circle work. The tangent of pi over 4. The coordinates at pi over 4 are root 2 over 2 and root 2 over 2. So if I take the y and put it over the x, I'm going to get 1 plus the coordinates at pi over 3 are a half root 3 over 2. If you take the y and put it over the x, you're going to get root 3 over 1 minus tangent pi over 4 again is going to be another 1. So that's not important. And tangent of pi over 3 is square root of 3. Okay, so now we're going to rationalize our denominator to try to get the radical out. By the way, the longer you go in mathematics, the more acceptable it becomes to leave a radical in the denominator. But for now, we'll go ahead and continue to remove our radicals. And since we have a 1 minus the square root of 3 in the denominator, remember the way to get rid of that is to multiply by the conjugate, which the conjugate of 1 minus root 3 is 1 plus root 3. Okay, so let's do some multiplying now. In the denominator, 1 times 1 is 1. Since I'm multiplying conjugates, I don't have to worry about the middle terms because they're going to cancel. So if I take negative root 3 times positive root 3, I'll get negative 3, which will give me a denominator of negative 2. In the numerator, 1 times 1 is 1. 1 times root 3 is root 3. Root 3 times 1 is root 3. Root 3 times root 3 is 3. So I have 4 plus 2 times the square root of 3 in the numerator. I could factor a negative 2 out of that numerator, and that'll leave me with negative 2 minus root 3. And the value of doing that, then I could get the negative 2's to cancel. So what's the tangent of 7 pi over 12 equal to? It's equal to the negative 2 minus the square root of 3. By the way, notice on that problem, most of your work, especially from here on out, is algebra. And that's going to be true in calculus as well. The calculus part of a calculus problem is small. The algebra part of a calculus problem is large. Okay, then we've got some cofunction identities sitting here. Cosine of 90 minus theta is equal to sine of theta, and all these others. We're not going to use these very much. You might see them sometime again used in a different class, but not very often. So we're not going to spend much time on those. But what we are going to do are these kind of problems like I have the last several examples here, where it says write cosine of 180 minus theta as a function of theta. Well, what does that mean to do? Well, it means just to go ahead and apply the difference identity for cosine and see what you get. The cosine identity goes cosine of the first, cosine of the second, and remember the sign flips on cosine, plus sine of the first, sine of the second. Alright, well, cosine at 180 is negative 1. Negative 1 times cosine theta would be just negative cosine theta. Sine at 180 is 0, so 0 times sine theta is 0. So to write it as a function of theta means we just want something with a theta in it. There it is, negative cosine of theta. If we were going to do the same thing down here with this sine problem, I'd apply the sum identity for sine. Sine 180 cosine theta plus cosine 180 sine theta, and simplify. Sine at 180 is 0 times cosine theta is 0. Cosine at 180 is negative 1 times sine theta would be negative sine theta. So this would be equal to negative sine theta. Okay, it's not so bad. So the rest of these are going to work in similar fashion. The one I want to go ahead and take a look at is this tangent one, because sometimes tangents, the algebra on them gets a little messy. So let's go ahead and knock that one out to finish off this section. So tangent of 45 minus theta would be tangent 45 minus tangent theta over 1 plus tangent 45 tangent theta. And again, all I did was apply the difference identity for tangent. So I applied this identity right here. Alright, now let's see what we got. Tangent at 45 is 1 because the coordinates are root 2 over 2 and root 2 over 2. So in the numerator I have 1 minus tangent theta over, and on the bottom I've got 1 plus tangent of 45, still 1 down there. So I end up with 1 minus tangent theta over 1 plus tangent theta. And that's about all we can do with that. So there's you a quick video. Now I did that kind of fast, so if you need to pause and go back and rewatch or from time to time, that's the beauty of a video, you can do that. And we'll get you another video on 7.4.